All right, hey, some applied problems that will require us to use exponents and logarithms. All right, so let me erase this here. Okay, I'm going to start off with the classic. The classic is radioactive decay. I would normally go over what radioactive decay is, but since you're probably at home and have a lot of free time, you can look it up. Roughly speaking, it's when the nucleus of an atom cracks apart into two or more pieces, and that would be fun to talk about, but let's try to keep this video short. I'm going to go on the assumption that you roughly know what it is. And I'm going to write down an equation now. Let me go ahead and write it down. This is one of the most famous equations and important equations in all of math and science and engineering. It goes by a lot of different names. Its formal name is called the natural law of growth and decay. I'm not going to use that expression again. It deals when things either undergo exponential growth or exponential decay. And in the case of radioactive materials or radioactive isotopes, you don't know what an isotope is, look it up. Two atoms are isotopes. They have a different number of neutrons, same number of protons, but when an atom undergoes radioactive decay, it's no longer the same type of atom. So really, it's material. It's all this. Well, look, it undergoes decay. You have less of it than when you started with. So you could sort of imagine maybe you had 100 atoms of the same type. And if they undergo radioactive decay, as time goes on, you have fewer and fewer of these atoms. See, again, I'm trying to rush these concepts, so it's better if I assume you know what they are. And if you don't know what an isotope is or radioactive decay, or you're not familiar with the nucleus of an atom or the structure of an atom, just go to YouTube and search those things. You'll find plenty of good stuff that'll explain it all. This equation right here has, well, I don't know how many uses, hundreds, thousands, definitely thousands. So this is just one example, and I think it's probably the most classic example, and it's a great first example. What does everything here stand for? This right here stands for the initial amount, or the beginning amount. So A for amount and the sub-zero, 0 for time 0. T stands for time. I'll get to E and K in a second. This is the ending amount. So you have a beginning amount, a period of time which goes by, and an ending amount. This is the beginning amount, ending amount. T is the elapsed time, or the time that has gone by. What is K? K is a constant. And all these letters are fairly traditional choices, with one exception I'll get to in a second. You don't have to use K, but K is a pretty classic choice. K will determine the rate at which something decays or increases. Or, rather, actually, K is determined by the rate at which something decreases. Now, so this gets called different things. It gets called different things depending on what we're doing. And the next video, I'll do another classic example, which is how money grows in a bank. Now, in a bank, K turns out to be the interest rate. If it's a drug, and I'll do this example too, like you take aspirin or caffeine or morphine, and drugs are eliminated or metabolically change into other things in the body, but at any rate, they're eliminated, and in medicine case called the elimination rate. But here with radioactive isotopes, this is called the decay constant. Now you don't have to know decay constant, but that is what it's called. And so again, K gets referred to in words differently depending on what we're doing here. Now, what is E? I haven't mentioned E before, not in this course. And if you know what E is, it's because you learned it somewhere else. E is a number. It doesn't change, and we never solve for E. So E is a fixed number. It's approximately 2.7. The E stands for Euler, EULER. He's a famous Swiss mathematician who came up with so many things I wouldn't even know where to begin. He was blind, at least I think after his childhood. He wrote something like 70 volumes of mathematics, very advanced mathematics. And E is in his honor. E is one of the most important numbers in mathematics. It's more important than pi. It's profoundly important. If you look at any calculator, you'll see a button with this lowercase e on it. So E is sort of a holy, a special, reserved symbol that's used just for this. Now, a couple of questions you should have. Where on earth did this equation come from? I'm absolutely not saying. If you take a pretty serious calculus course, you'll find out. You'll find out where this number comes from, and you'll find out how it gets, how did it come to be in this particular equation. You solve a nice, relatively simple differential equation, something I could do in my calc classes. But here I'm saying you have no choice right now. Just for right now, this is a terrible thing for me to say, but you got to take my word for it that this works. It's a terrible thing for me to say. If it was a good physics class, we would do an experiment and test to see that this actually works. Now, of course, it's been tested countless times, and it absolutely works. But nonetheless, it's kind of an interesting thing to see. I can remember doing it many moons ago. Okay, now let me give you a type of problem that we're going to do. Let me give you an actual problem that we'll do. Wait, I don't know why I erased. What the heck? Why did I erase this T? E to the KT. Again, the formal name of this equation is the natural law of growth and decay. Sometimes people call it the exponential equation, like with a capital T. But we don't have to call it anything. Now, suppose that, how about this? Suppose that you work in a nuclear power plant. How about the Fukushima reactor in Japan? That might have been so long ago that you don't remember, but there was the tsunami and a catastrophe, and radioactive isotopes were released in the environment. Let's suppose, hey, you know what, let me back up, because otherwise we're going to have to make another assumption. Let's suppose we have a radioactive isotope. We don't know anything about it, but what we do is we measure the initial amount of this radioactive isotope. Let's say we measure 10 grams, and then we let some time go by. So let's say now as long as I keep the times consistent, it doesn't matter, years, millennia, century, nanoseconds, weeks, whatever you want to call it. Let's say, I don't know, we'll say days, okay? We let 20 days go by, and we measure how much we have left, and let's suppose we have 9 grams. So we start with 10 grams, and we let 20 days go by, and we have 9 grams. This information right here could only be gotten empirically, which is to say you have to do an experiment. How would I know these 3 things? You'd have to do an experiment. How will you know these 3 things? I have to give you this information. So let me repeat that. I have to give you this information. What's the question? The question is, what is the decay constant? And here's how we figure it out. Let's plug everything in this equation that we know. We ended up with 9 grams. We started with 10 grams. Remember, E is a fixed number. It's a constant. It's called the base of the natural logarithm, blah, 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 blah. But the point is, it's a number. It doesn't change. We don't solve for that. E to the K, we don't know. And T was, what did I say, 20. We need to solve this equation for K. So let me just go ahead and I'll show you how to solve it. Let's divide both sides by 10. You could write 0.9. That's fine if you want to do that. Now, what I'm going to do, this is a new thing. 2 videos ago I mentioned logarithms, or maybe it was last video I mentioned logarithms. We're going to take a logarithm on both sides, but not any logarithm. Well, we could actually use any logarithm, but what I want to do is I want to take the logarithm with base e on both sides. And you'll see in just a second, there's a reason for this. What is this right here? You don't need to worry about that one bit, and I'll tell you why. How are you going to figure this out? You're not. Your calculator is. So I think this is really the first time we're absolutely not only going to want to use a calculator, but for right now, you're going to need a calculator. And if you get to Calc 2, you won't need a calculator, but you sure will want one, and you'll always use one anyways. But for right now, the only way that I'm going to show you how to do this is by using a calculator. What's this over here? Well, if you look at the definition of a logarithm, these cancel each other out. I'd like you to go back and look at the definition of a logarithm and see what it has to say about this. And this is 20k. And that's why I'm using a logarithm with base e on both sides. So this is the logarithm of 9/10. You don't need the parentheses there. Base e. Is this still visible? Yeah. Hey, and let's divide both sides by 20. And so what you get here is you get k is equal to this, which is a number, a logarithm of 9/10, where the base is e, divided by 20. Now, calculator comment. On every calculator that's worth anything, you won't see a logarithm with base e. There's a shorthand for this, and it's written like this, the letter L and the letter N. So you'll see this button LN, almost always lowercase l, lowercase n. This has a name, and it's a name you want to know. It's called the natural logarithm. If you were to pursue a bunch of physics or chemistry, biology, engineering, what you would see is that this particular logarithm here, it arises naturally in a lot of different situations, science, engineering, economics. So it's called the natural logarithm. I mean, originally it came up, Euler was analyzing a particular problem in mathematics, and you can, again, find that out if you take calculus, which I hope you do sooner or later, but if not, so be it. So what you do is you use this button right here, 9/10. The parentheses is probably not necessary, but I think it's a safe plan to use the parentheses. A lot of calculators, once you press ln, that first parentheses will come up, and then 9/10, and then just divide that by 20. Now, in this particular case, you're going to get a negative number. Do I have a calculator nearby? No, I don't have a calculator nearby. But you will, I know it'll be a negative number. We should probably go over how the heck do I know it's a negative number? Well, one reason I know is whenever something is decaying, you're getting less and less and less of it, this will be a negative number. If you're getting more and more and more, this is a positive number. And I'm going to do some other examples. I'll do one from biology and one from banking, and who knows what. I'll throw some other examples in there. But at any rate, go ahead and calculate that and see what you get. Just a second. Give me a second. You know what I'll do is I'll go. Did I just erase it? Oh, there it is right there. There's our value of k. I could make up a value right now, but maybe that's not such a good idea. So hold on a second here. Let's see. Yeah, I mean, I just right now I just Googled calculator, and sure enough, of course, there's a button ln. If I didn't see that, I wouldn't even bother with it. Where's my answer here? Okay, so we'll probably have to talk about rounding off. For right now, I'm gonna make an arbitrary rule in class. You can feel free to round off to 2 decimal places. That's a completely arbitrary rule just to make things easier. But I'm getting negative 0.11. What I see on the screen here is negative 0.1053651. It's almost certainly an irrational number. Hey, e is an irrational number too. So the only way to write e is e, so it's approximately 2.7. Okay, so this is approximately negative 0.11. Now let's go back to, we worked in Fukushima, there was a terrible disaster, and let's say 100 grams was released in the environment. Everybody runs for their lives, terrible. And we know it won't be safe to go back into the building, let's say until, I'm just making these numbers up, let's say until there's 0.3 grams. So everyone runs for their life, and we don't want to go back into this building until there's no more than 0.3 grams of this radioactive isotope in the environment. The obvious question is, how long do we have to wait? And here's how we determine that. I don't want to forget this, but I want this out of the way. So K was negative 0.11. Let's plug everything we know into this equation. We want this to be 0.3. At the end of the time period, we would like to have no more than 0.3. We started with 100. E to the K was negative 0.11, and T is the unknown. How do we solve for T? Honestly, the exact same way we solved for K a minute ago. Let's divide both sides by 100. And I'm going to take the natural logarithm on both sides. Now I'll write it like this. This is L N. Remember, I'm not worried about this. We'll do this with the calculator. So you have no concern over that. And then the natural logarithm of e to the negative 0.11t. These two cancel each other out. And you don't have to show all these details if you don't want to. And divide both sides by negative 0.11. So t is equal to the natural logarithm of 0.003 divided by negative 0.11. And here, I'll go ahead just for the sake of completeness. Let me throw that into calculator. It was at 0.003. Okay. Whoa, wait a minute. I almost made an error there. What are we dividing by? Negative 0.11. If I'd rounded off to negative 0.1, it'd be a lot easier to. Oh, interesting. Wait a minute. Oh, whatever online calculator is definitely kind of awkward. Okay, so 52.8. So 52.8. Well, that can't be right. Somewhere along the way I've made a silly mistake. Let me see if I can find out where. Wait, it said 100 grams. What I get is 52.8, but that doesn't strike me as being right. So I think I've made a silly mistake somewhere. I worry because it's whatever this online calculator is here. Hey, I hope we said this was the right. I don't want to have to go back and redo it, but negative 0.11 was K. Let's see if I put everything in the right spot here. We want 0.3, 100. I divided by 100 so we can move the decimal place over 2. So there we go. Natural logarithm on both sides. These two cancel each other out. We divide by a negative 0.11. Maybe this is the right answer. The first part of this I did where I said we started off with 10 grams, and I think I said we let 20 days go by, and we had something's not right here. Wow. Oh my gosh. Okay, let me go back to the original problem because I want to double check the calculation here. I don't want to throw you off here with an erroneous calculation. I think I said we started off with 10 grams, we wound up with 9 grams. We don't know K, and that was after 20 days, as I recall. We'll divide both sides by 10, take the natural logarithm on both sides, so that's 9 divided by 10 is 0.9, right? And then we'll divide by 20. So that's K. So first let me just double check. By the way, this is an easy thing to do. It's incredibly easy to. Your fingers could just press the wrong button here. So natural logarithm of 0.9. And then, divide by 20. I wonder if I divided by, you know what? I don't think I divided by 20. Let me see here. Yeah, I didn't divide by 20. Oh, I forgot to divide by 20. So it's negative 0.005. Yeah, it's very different. Negative 0.005. Maybe in a later video I'll tell you how is it I just knew the answer I was getting was wrong. I knew it wasn't reasonable. It didn't mean I knew what the right answer was, but I knew it was wrong. Okay, so there's K. Now where's that going to affect everything? Well, I have to put the new K in there, and there, and there, and there. And so finally, the new K would be right here. So it should be negative 0.005. Now let me go ahead and calculate that, and we'll get the correct answer here. So natural logarithm of 0.003. And then we have to divide. Don't forget to divide this time. 0.005, negative 0.005. Yeah, okay, so 1,161. Yeah, 1,161. I mean, I'm just rounding off the nearest day. Say, actually, if I round off the nearest day, it's 62. And if it was a real world, I'm going to let a little extra time go by, just play safe. So, about 3 years. Okay, this equation right here, I'm going to do next video. I'll do 3 or 4 more real world examples. Is this real that I just showed you? Absolutely. When it comes to radioactive isotopes. In fact, the next video, I want to go over what's called carbon-14 dating, and you can see how it is that we can determine, this bone that we dug out of the ground is, I don't know, 32,000 years old. Okay, so that's it. That's enough for this video.